All right, let's go ahead and get started. First things first, just to remind you, in case you've forgotten, that your homework number 3, test review number 3 is, you have a link to it right down here. And it is due by Thursday, March 29th, so a week from now. Always trying to get this stuff to you guys to your on the early side. You are to submit all your answers in Canvas. And under the modules, under the homework number 3, test review 3 link, you are to also turn in the free response part number 2 of your homework number 3, test review number 3 on Thursday at the beginning of class. Which means that your test 3 is going to be on Tuesday, April 3rd. Just FYI on that one. Now, what I'm saying here is this. It's just like before. You come all the way down here, because we're getting towards the end of the class type thing here. We're finishing up 3.5 today and moving on into section 3.7. So hopefully you've already done the 3.7 quiz. And here is your homework number 3, test review 3 link. And when you click on this thing here, you've got my same information. I talk about submitting your answers and all that other good stuff. Here's another way of getting the blank copy of this thing for you guys. And remember, it's recommended that you do and treat this review as just as if you were taking a test to help better prepare you guys for the actual test. And I get to review it, but you guys actually, you'll see that each question on this thing is there. I've got it linked in the Canvas, and you're supposed to actually go on the multiple choice, fill out the multiple choice, even in the free response, either put in the answer or I made it a multiple choice kind of a question or whatever. And so it's all there, so you have to do this. And then on the free response part, and here's a copy of it over here. So this is what your homework set number 3 looks like, and of course it's first part of it is 3.1, 3.2 algebra review for at least the first couple of pages of it. And then eventually I actually start getting into some derivatives and compound interest and some of the formulas. It's all kind of intermixed, but a bunch of derivative stuff here that we'll be doing. And I made them multiple choice kind of questions here. And you keep on going. So there's 20 multiple choice questions on this thing. And then here comes the free response. This is the part I want you guys to turn in to me. This will be on Thursday the 29th. And so, and remember, just like before, we're doing more derivatives, so label your derivatives. I'm throwing some very complicated formulas at you guys, doing logarithmic differentiation, another logarithmic differentiation, and this is the 3.7 doing the L'Hopital's rule type stuff here. Here is a population growth kind of a problem here, and here is a Newton's law of cooling kind of a problem here. So it's a great review for what you guys are going to do on the test. I've also instructed my preceptor Katrina on the review tomorrow. If you guys happen to have any questions on this thing or want some assistance on it, besides web work questions and stuff, she's more than happy to help you guys out with that. Again, this is on tomorrow's at the review session at 3:30 in the afternoon and stuff. So main thing is get this thing done. It is due, like I said, before class or right at the beginning of class on Thursday the 29th. And I will be making a video, or we have a video of solutions for you guys to study over the weekend for, because your test is on that following Tuesday. So there we go. The problem is I usually have you guys do this stuff on Friday, but Friday, March 30th is actually Good Friday, so the school is closed. So I had to make another plan. And so it's going to be due the day before the 29th and stuff right at the beginning of class. All right. Questions? All right. What we were doing last time, we were talking about inverse trig. And I know trig has a way of scaring a lot of people and stuff like that. But the main thing you guys need to know about trig is, number one, that unit circle stuff. When they say exact values and they want to know what the cosine of 2 pi thirds is, you should tell them -1/2. You should be able to read that thing in your mind as well as be able to generate it if you don't actually have it memorized right off that unit circle stuff. And we're focusing on the inverse trig, and we did it on the inverse trig in terms of the unit circle. So with sine inverse, tangent inverse, and cosecant inverse, you use the right half of the unit circle with The fourth quadrant being negative angle quadrant, negative pi 6, negative pi 4, negative pi thirds, negative pi halves. And you use the top two quadrants, first and second quadrants, for cosine inverse, cotangent inverse, and secant inverse. So the restricted unit circle stuff here. But now these inverse trig functions are formulas. Now this I cut, copy, pasted literally right out of your textbook. These are your basic derivative formulas for the inverse trig formulas. The derivative of sine inverse of x is equal to 1 over the square root of 1 minus x squared. The derivative of the cosine inverse of x is negative 1 over the square root of 1 minus x squared. The derivative of the tangent inverse of x is 1 over 1 plus x squared. The derivative of the cosecant inverse of x is negative 1 over the x times the square root of x squared minus 1. The derivative of the secant inverse of x is 1 over the x times the square root of x squared minus 1. And the derivative of the cotangent inverse of x is negative 1 over 1 plus x squared. But you guys learned from section 3.3, when I introduced those logarithmic and differentiation formulas, that at this point in your career of calculus, every time we go over a rule, there's the basic rule, and then there's a chain rule version of that rule. And I'm going to write all this stuff out for you guys. But you look at this stuff and you go, how in the world is the derivative, for example, of the sine inverse of x 1 over the square root of 1 minus x squared? Is there a pattern for this thing? Well, number one, yes. So I'm going to show you that pattern. Because I think it's always important that for you guys to understand where the formulas come from. I mean, at the end of the day, you're right, your job in life is to memorize everything. You're calculus students. And so you're going to memorize the formulas, but it's nice to know where they come from, so if you ever forgot something or other, you can at least regenerate it. So here's the deal. I have y equals the sine inverse of x, or you can write this as y equals the arc sine of x. It's the same thing. This is the old Greek way of denoting it. And modern math, we call it sine inverse of x, or the arc sine of x. Same thing. Now, why is the derivative what it is? Let me prove it to you. Well, this is equivalent in saying, well, what gets rid of a sine inverse? What's the opposite of an inverse function? Well, it's the original function itself. So if I take the sine of both sides, and I'm going to show you this. I take the sine of y equals the sine of the sine inverse of x. The sine and the sine inverse will cancel each other out. And that leaves you with the equation, the sine of y equals x. It's the same thing. This, y equals the sine inverse of x, is the same thing as the sine of y equals x. I just moved the sine to the other side and got rid of the inverse. That's what inverses do. It pushes the function on the other side. So, here's the deal. Take the derivative of this guy here. The sine of y equals x. I want you to take the derivative with respect to x. And this would be implicit. Which means every time you take a derivative of a y function, because y is not actually solved for now, you got to tack on this dy over dx. So, what is the derivative of the sine of y? What's the derivative of sine function? Cosine. So derivative of sine y would be the cosine of y times, chain rule, the derivative of the inside, derivative of y would be dy over dx. So every time you take a derivative of y, you got to tack on that dy over dx. Equals, what is the derivative of x? In case you can't read my x there. What's the derivative of x? With respect to x is 1. Which means when I solve for dy over dx, I get dy over dx is equal to 1 over the cosine of y. There's my answer. Well, geez, Dr. Taylor, that doesn't look like those weird formulas you came up with. Well, let me explain how you get those formulas. But note, the original function was this guy. The sine of y equals x. It is right triangle trig. And what you should have remembered from your junior high school math class, trig class, whenever you guys took trig, was this. Now, every teacher you ever have, and whenever you take math, has their own way of doing stuff. And so most of you guys probably know when you were supposed to memorize the relationship of the trig functions, you guys came up with some kind of weird mnemonic, Sakatoa or something weird like that. You guys know what I'm talking about? Sakatoa? Well, see, here's my problem. I'm real good at math, but spelling, English, poetry, no, I don't do that. And so I can barely speak English, more or less write it down. And Sakatoa, I couldn't spell that if I tried. P-H-Y something, I have no idea. So my teacher had to come up with a different way of memorizing this stuff. And this is how I memorized it. If you look at any calculator ever made since the beginning of handheld calculators back in the 50s and stuff, the buttons on the calculator are always the same. With the trig functions, they're always sine, cosine, tangent. Always in that order. So that's just an order I memorized. Sine of an angle, cosine of an angle, tangent of an angle. Okay? And in that order, here is the ratios. Oh, heck, another hour of algebra. That's how I had it memorized. Which means what? The sine of theta is equal to the opposite over the hypotenuse. The cosine of theta is the adjacent over the hypotenuse. The tangent of theta is the opposite over the adjacent when you do a right triangle trig. And if you focus on one of the corners being the angle, it's right triangle, the straight across is the opposite side. The side that touches the angle is called the adjacent. Obviously, the side opposite the 90 degrees, the longest side, is called the hypotenuse. This is your relationship of right triangle trig. Now, again, my teacher came up with lots of mnemonics for us. I also remember the Sakatoa, but like I said, my class, I couldn't spell that because I have no idea how to spell Sakatoa. I know it now. It is S-O-H-C-A-H-T-O-A, but the only way I know that is because I have this written down. Okay? But you can also figure out what generation my teacher was in because she also came up with some other mnemonics. I remember this one. Some old hippie caught another hippie tripping on acid. Yeah, that was definitely 1960s. My teacher's was from, I don't know, Woodstock or something. I have no idea. But the main thing is, I don't care what it is, you got to have memorized. This is what you really need to know about right triangle trig. Okay? So, what we got here is this. The sine of y equals x. I'm going to make x a fraction. I'm going to make him x over 1. Y is the angle referred to as theta up here, and because this is a sine, the x is the opposite and 1 is the hypotenuse. So this is going to actually generate a very special right triangle. Y is the angle in the corner. The angle is y. The opposite side is x. The hypotenuse is 1. And there's one side that I don't know. I need to figure out what that guy is. What major theorem do you know that connects all the sides of a right triangle? Pythagorean Theorem. The old a squared plus b squared equals c squared. The sum of the squares of the sides of a right triangle is equal to the square of the hypotenuse. That's the big theorem there. Okay, but you guys know it better as a squared plus b squared equals c squared. Fine, write it down. Question mark squared plus x squared is equal to 1 squared. Pythagorean Theorem. Solve for the question mark. Well, question mark squared plus x squared equals 1 squared is 1. I'm going to subtract x squared from both sides. That gives me question mark squared is equal to 1 minus x squared. And what kills off a square? Square root. Now under a plus or minus you can't distribute a square root. Only through strict multiplication division can you break it up. That's a minus. I've got to leave it like it is. And because this is a triangle, it's a distance, we take the positive square root because this does represent a triangle. So the question mark is the square root of 1 minus x squared. Square root of 1 minus x squared. Does that make sense? That's what the question mark is. Now, do you remember our answer when we did implicit differentiation for the derivative of the sine inverse of x way back up here? What I did was I moved the sine to the other side and did implicit differentiation of sine y equals x and ended up getting a cosine of y times dy over dx equals 1, and solving for dy dx, I get dy dx equals 1 over the cosine of y. Now I want you to look at this triangle right here and tell me what is the cosine of y equal to. The cosine, by definition, is the adjacent over the hypotenuse, right? Here's my triangle right here. What's the adjacent? What's the adjacent side? I'll blow it up and you guys can see it in the back. What's the adjacent side? Here's angle y right there. What's the adjacent side? Square root of 1 minus x squared divided by what was the hypotenuse? 1. So in other words, the cosine of y, when you clean them up, is just the square root of 1 minus x squared divided by 1. No one cares. So now I can take this and go back and plug him in here and get dy over dx is equal to 1 over the square root of 1 minus x squared, because that's what the cosine of y equals. And there is the proof of why the derivative of the original function, which was y equals the sine inverse of x, is 1 over the square root of 1 minus x squared. You can do the same thing for the tangent inverse or the secant inverse or any of them. What you do is you move the function to the other side, take the derivative of it implicitly, and then solve for the dy over dx, and then go draw your triangles on the original equation to figure out the ratio of the sides, and then go back and replace whatever trig function you got with its ratio. Does that make sense? So if I do one, I can do them all. This is the proof of what the formulas are or what they are. Now, my math majors in here, they're excited about anytime seeing a proof, as they should be. But the rest of you people, you're real happy with the fact that you now need to know and memorize. The fact is that the derivative of the sine inverse of x is 1 over the square root of 1 minus x squared. Okay? At the end of the day, that's what you really got to know. We're not going to quiz you on, write up the proof for us. Math majors will get you that later, but not here. We're just going to know what the formulas are. The derivative of the sine inverse of x is 1 over the square root of 1 minus x squared. There are 6 trig functions. Therefore, there are 6 trig inverse functions. You've got to memorize all of them. But then people go, well, that's kind of monumental, Dr. Taylor. I got enough things to memorize in my life. I don't need to memorize all this. Well, yes, you do, because it's your life. You're a science major, so there you go. But there's a pattern to this. Have you caught the pattern yet? Let's go through the pattern back in regular trig. What's the derivative of sine of x? Cosine of x. What's the derivative of cosine of x? Negative sine of x. What's the derivative of tangent of x? Oh, that's sad. I could hear crickets in here. Come on. What's the derivative of tangent of x? It's things we have memorized. Secant squared of x. What's the derivative of cotangent of x? Negative cosecant squared of x. What's the derivative of secant of x? Secant of x. Secant of x, tangent of x. What's the derivative of cosecant of x? Negative cosecant of x, cotangent of x. Things we have memorized from chapter 2, right? Trig functions. What was the pattern? Because I taught you guys the pattern. Every time you took a derivative of a cofunction, it was always what? Negative. Well, take a look again. Inverse trig doesn't change. What's the derivative of the sine inverse of x? It's 1 over the square root of 1 minus x squared. What's the derivative of cosine inverse of x? It being a cofunction and all, it's negative 1 over the square root of 1 minus x squared. What's the derivative of tangent of x? Tangent inverse of x. It's 1 over 1 plus x squared. What's the derivative of cotangent inverse of x? It is negative 1 over 1 plus x squared. It's the same thing, but every time you take a derivative of co, it's negative. What's the derivative of secant inverse of x? It's 1 over x times the square root of x squared minus 1. What's the derivative of cosecant inverse of x? Negative 1 over x times the square root of x squared minus 1. So what's the pattern? Every time you take a derivative of one of these cofunctions, that means cotangent or cosine, cotangent or cosecant inverse, they're all going to be negative. So how many of these guys do you actually have to have memorized? 3 times 2, because the chain rule I'm about to show you guys. So, but that's it. So it's not as many as you think, as long as you guys can catch a pattern on this stuff. And that's always been the key of mathematics, is catch a pattern with this, and you can utilize that pattern to make sure you make A's on tests. So, here we go. Another nice sheet of paper here. I'm going to do with you guys what I did with you guys when I did the inverse trig functions. I'm going to write down all the rules. The basic rule, and then there's a chain rule version of that. Again, this is discussed in the book, but not literally thrown in your face like I'm trying to do it here. So, here we go. Trig inverse derivatives. Okay? That's a beat. Okay. Number 1, if y is equal to the sine inverse of x, what's the derivative? We just did it. We proved it too. 1 over, what was it? Square root of, order matters, 1 minus x squared. Number 2, if y equals the sine inverse of a function, something other than x, you're going to get the same pattern on it, but chain rule, quote unquote, times the derivative of the inside. So you get this. So y prime would be 1 over the square root of 1 minus the function, instead of just x squared, times in the back the derivative of the inside, the chain rule version of it. Number 2, if y equals the cosine inverse of x, you caught the pattern y prime equals negative 1 over the square root of 1 minus x squared. It's just negative of what you got with the derivative with the sine. And number 3, was 3, sorry about that, 3, this would be number 4, I can't actually count. Y equals the cosine inverse of a function, you get y prime equals negative 1 over the square root of 1 minus the function squared times the derivative of the inside. It's the same thing except it's negative. So there's actually only 3 of these guys I'm focusing on. Just remember co means negative. Alright, number 5. If y is equal to the tangent inverse or arctangent of x, the derivative was what again? See if you have it memorized yet. Because this is calculus, you look at it for 2 seconds, you're supposed to have it memorized. What is it? 1 over 1 plus x squared. We expect you to have it memorized. So, number 6, if y equals the tangent inverse of a function, then the derivative is going to be 1 over 1 plus, catch a pattern, the function squared, but then times, in parentheses, what? The derivative of the inside. Chain rule version of it. Same pattern, but times the derivative of the inside. You put whatever you're taking the tangent inverse of down here and being squared plus 1 on the denominator times the derivative of the inside. Then, of course, you get 2 for free, number 7 and number 8. If y equals the cotangent inverse of x, then y prime equals negative 1 over 1 plus x squared. And number 8, if y equals the cotangent inverse of a function, then y prime equals negative 1 over 1 plus the function squared times the derivative of the inside. Same thing. And then there's just 2 more. Number 9, if y is equal to the secant inverse of x, then y prime equals 1 over x times the square root of x squared minus 1. All right, how do you have it memorized? Well, I've got sine memorized. Sine inverse of x, the derivative of that is 1 over the square root of 1 minus x squared. It's 1 minus x squared. So for the secant inverse, it'll be 1 over, there's an extra x out front, and they switch positions. It's the square root of x squared minus 1. Order matters. Does that make sense? And then, of course, you got the chain rule version of that. If y is equal to the secant inverse of a function, then y prime is equal to 1 over the function times the square root of the function squared minus 1, then times the derivative of the inside. And then you get 2 more for free. If y equals the cosecant inverse of x, being a cofunction, y prime is going to be negative 1 over x times the square root of x squared minus 1. And then number 12, if y equals the cosecant inverse of a function, something other than x, then y prime equals negative 1 over the function times the square root of the function squared minus 1 times the derivative of the inside. It's not as bad as you think. There is some memorization to be done, but if you catch the pattern, you don't have to beat your head against the wall to try to drum all these 12 formulas in there. It really is a pattern of co's or negative, so there's cut them in half, basically, is what you got to know. Does that make sense? So, Now that I've gone over these wonderful functions, let's do some problems. Now, hopefully you'll watch the awesome pre-section video some idiot professor did for you guys. And we did a bunch of these problems already. But, you know, it's good to practice. So let's do them again. All I'm interested in this stuff is actually the notation. What does d dx stand for? D over dx. Take the derivative with respect to x of what follows. That means these guys actually don't have names. So this will be the derivative of this thing equals, and you actually don't call it a name, you just write equals and write down the formula. If I ever tell you, and this is for homework and test purposes, if I give these guys names like f of x equals, and I ask you for the derivative, you better tell me f prime of x equals or df over dx equals. You got to label derivatives if they got names. If they don't have names, we use this notation. Well, 5 is a constant, leave it alone, times, what's the derivative of secant inverse of x? You got it memorized yet? Well, if you don't, just look up here. Secant inverse of x is 1 over x times the square root of x squared minus 1, plus, just a little practice on derivatives, what's the derivative of 2x squared? 4x, and derivative of 3 is 0, and I'm done. You officially could put 5 times as 1 over and put the 5 in the numerator, but who cares? This guy, number 10. Take the derivative with respect to x of 5 cosine inverse of 3x squared plus 5. You're taking the cosine inverse of this 3x squared plus 5. This is a chain rule because you got something other than x that's inside the quote-unquote parentheses of that cosine inverse. 5 is a constant. No one cares about 5. It just holds over. 5 times. Derivative of cosine inverse, being a cofunction, is going to be negative 1 over, this is the chain rule version of it, of the square root of 1 minus the function 3x squared plus 5, quantity squared, negative 1 over the square root of 1 minus the function squared times the derivative of the inside. What's the derivative of 3x squared plus 5? 6x. Now, if you want that back of the book look, we'll put it all together. This is being multiplied, and that negative 1 is a constant there. 5 times negative 1 times 6x, what makes it what? Negative 30x over the square root of 1 minus parentheses 3x squared plus 5 quantity squared. There's the derivative that looks like the back of the book. But personally, we're real happy if you can give us this. But remember, it's not minus, it's multiplication. It's 5 times the negative 1 over. Okay. Take derivative of the tangent inverse of 5x squared plus 17. Again, anything other than x means you got to use the chain rule version of it. It's the tangent inverse of a function. So the derivative of that is going to be 1 over 1 plus the function, which is 5x squared plus 17. The function squared, but then times the derivative of the inside. Derivative of 5x squared plus 17 is 10x. And if you want to, knock yourself out, write it as, to get that back of the book look, 10x divided by 1 plus 5x squared plus 17 quantity squared. But there's a lot of things we can do with this stuff. Product rule, chain rule, and quotient rule, because we're going to beat that to death with the exponentials, the logs, and now we got the inverse trig functions. Take a look at this guy here. F of x is equal to the tangent inverse of x raised to the 7th power. Pause, hesitate, and ask yourself, what do you see? I see function on the inside raised to that 7th power means this is a chain rule. Derivative of the outside, inside stays the same time derivative of the inside. So this has been labeled. So f of x equals tangent inverse of x quantity to the 7th power. So f prime of x is equal to chain rule. The derivative of the outside, the 7 pops out front. The inside, tangent inverse of x or arctangent of x stays the same. Raised to the 6th power. Don't forget that guy. Bring down your power and subtract 1. But the inside stayed the same. But then you do times the derivative of the inside. What's the derivative of tangent inverse of x? Pure memorization. 1 over 1 plus x squared. And there's my derivative. Does that make sense? Questions? Look at next one. Again, this one was labeled. Yep, and we're going to throw some exponentials at you. Good practice. f of x is equal to the cosine inverse of e to the 8x. Your mission, find f prime of x. So f prime of x, I pause, hesitate, this is the cosine inverse of something other than x, so this is function, so this is a chain rule version of it, but it is a cosine inverse, and being a cofunction, the derivative is going to be negative 1 over the square root of 1 minus, in this case instead of x, the function e to the 8x squared, but then you've got to do times the derivative of the inside. What's the derivative of e to the 8x? Well, again, you've got to use the chain rule on that. Derivative of e to a function is e to the derivative of e to the x is e to the x. Derivative of e to a function is e to the function times derivative of the exponent. So what's derivative of e to the 8x? E to the 8x times the derivative of the exponent, which is 8. Again, you can clean this guy up and make it look like the back of the book. This would be negative 8 e to the 8x divided by the square root of 1 minus e to the 8x quantity squared. Or, some back of the books beat it up to the point that you can't recognize it. A power to a power. What do you do with powers? Now, try again. Power raised to another power. You multiply. Two like bases being multiplied, you add their exponents. But something with a base raised to a power and then raise that to another power, you multiply the powers. So what is 8x times 2? 16x. And this is what it would look like literally in the quote-unquote back of the book if you cleaned it up to the umpteenth degree. Does that make sense? All right. What is the limit as x approaches 1 from below of the sine inverse of x? Sine inverse of x. When I'm dealing with sine inverse or tangent inverse or cosecant inverse, I only use the right half of the unit circle. Here is, pi 6, pi fourths, pi thirds, pi halves. Down here in the fourth quadrant, there's negative pi 6, negative pi fourths, negative pi thirds, negative pi halves. If you look at these points here, these points are, I'm just going to do the ones in the first quadrant because they're positive. This would be the square root of 3 over 2, 1/2. Square root of 2 over 2, square root of 2 over 2. 1/2, square root of 3 over 2. And the point up here is x is 0, y is 1. This point right here is the point. This is 0 would be the point 1, 0. And then I do the same thing down here, negative. The y coordinates are negative. But we're going after, what number are we going after? 1. And remember, the y coordinate is the sine of x. So I'm looking for the, remember, also, the sine inverse of a number is going to give you an angle back again. We're looking for an angle. And for us, the angles are going to be in radians unless otherwise stated in degrees. On web work, you'll notice they'll put a blank and then a pi. There's a clue because the radians always have pi in the answer. You just have to put in the fraction and stuff. So here we go. We're going after 1. And remember, we're talking about sine here, sine inverse. So where's the y coordinate equal to 1? It's right here. As we approach 1 from below, we're approaching 1, going from, basically we're going from square root of 3 over 2, which is 0.8660, all the way up to 1. What angle are we approaching? What is the angle associated with the point 0, 1? The answer is pi halves. When you take the sine inverse of a number, you get an angle back again. Yeah?
So if you tried to approach it from the other side, would it not exist?
Exactly. Why would it not exist? Because remember, we have to use this restricted unit circle. So the restricted unit circle on this thing is a number between, and if you think about it, these are numbers between, angles between, negative pi halves and positive pi halves. But if you look at the sine function, it bounces between what two numbers? 1 and negative 1. And you can never be above 1. So if we put a plus on this thing, answer does not exist because you don't go above 1. Sine bounces below. Up to 1 and then back down again. Down to negative 1 and then up again. So bounce between negative 1 and 1. So anything above 1 would not exist. What about this guy here? Now this goes back to some other stuff. See if you guys have memorized. So there's lots of things to do on this one. But let me just remind you of things you're supposed to have memorized already. Help me out here. What's e to the infinity? Infinity. What is e to the negative infinity? 0. What is the natural log of 0 on the plus side? Because you can't take the log of a negative number. You remember? Oh, that's sad. You better get this in your notes then if you guys don't know this. This is from chapter 3.2. Negative what? Negative infinity. Think about what your log graph looks like. It goes straight down. Negative infinity. What is the natural log of positive infinity? Infinity. Okay. What is 1 over infinity? This is from chapter 1. 0. And that doesn't matter, plus or minus. All right. What is 1 over 0 from the plus side? 1 over 0 doesn't exist, but 1 over 0 on the plus side is actually positive infinity. 1 over 0 from below is actually negative infinity. Right? Oh, not done yet. What is the tangent inverse of infinity? As I blow up, we talked about this last time. If I go straight up and this tangent goes towards infinity, what's the tangent inverse of that infinity? Gives you what angle? It's an asymptote. Well, remember what it was? Pi over, good. Pi over 2. And then the tangent inverse of negative infinity is negative pi over 2. Remember, because we went through all these things before. All I'm doing is just stating other facts. Now, when we give you a problem like this, you're going to have to connect all this information together. So you need to know this. What's the first rule of limits? Day 1 in this class. First rule of limits is plug it in. So when I take the limit as x approaches infinity of the arctangent of e to the negative e to the x, you plug it in. This will be the arctangent of negative e to the infinity. Now work your magic. What is e to the infinity? E to the infinity was what? Infinity. And what is the arctangent or tangent inverse of negative infinity? Because of that negative out front. What is it? Negative pi halves. And there's your answer. All I did was follow my nose, but I have this memorized. Does that make sense? Yes, calculus has got a bunch of memorization in it in terms of knowing the patterns of functions. And Calc 2 will get a lot worse in terms of how much you got to have memorized. Okay? Questions? Did I lose you guys anywhere? Okay. So hopefully you can go back and do any of your web work problems and the like. And if you've got problems on web work, that's what Fridays are for. We'll go over that with you guys as well. But we're moving on. Chapter 3.7. Chapter 3.7 is about a very important concept. And that is called L'Hôpital's rule. The hospital rule for the rest of you people, but it's French, so it's L apostrophe H. H is not it's silent in French, so L apostrophe H-O is L'Hôpital rule. Okay? Named after L'Hôpital is actually a person's last name, so it's not the hospital rule. It doesn't have anything to do with hospitals, except if you don't know how to do this, you will probably die. So, very important to get this stuff down. Now, here's the deal. This is going to be one of those topics that come back and haunt you. Not just in this class, because we're testing you on it, but you'll see it again in Calculus 2. You will see it again in Calculus 3. You'll see it again in differential equations. It will continuously haunt you with anytime you're doing any kind of real limit problems. Okay? If you remember, when we were in chapter, 1.3, when we were doing limits, first rule of limit, plug in a number. If you get a number, you're done. Second rule of limits, you plug in a number and you get the famous 0 divided by 0. What were you supposed to do? You remember? Algebra. There was some kind of weird algebra. You would have cleaned this thing up and then replug in the limit. Anytime you had 0 over 0, you were supposed to do algebra if possible. Those are my exact words. Go watch the videos. You'll hear it again. If you plug it in, you get 0 over 0. 0 over 0 is very special. This is one of those indeterminate forms. And L'Hôpital, back in the early 1700s, came up with a pattern for this, and thanks to the knowledge of the derivatives and stuff, could apply the derivatives to these cases and make it a little bit easier for you guys to get the answer without having to do algebra. Okay? So, if we have a limit of the form limit as x approaches a of f of x over g of x, where both f of x approaches 0 and g of x approaches 0, then we have the indeterminate form of 0 over 0. We also had another indeterminate form. That was in chapter 1.6 when we did the limits as x approaches infinity and we got infinity over infinity. Now we did some weird stuff about the degree of the top over the degree of the bottom, and you can figure out, you know, the answer was either plus or minus infinity. If the degree of the top equals the degree of the bottom, then the answer was the ratio of leading coefficients. If the degree of the top was less than the degree of the bottom, then the answer was 0. We had some properties on that stuff. Infinity over infinity is still considered what we call indeterminate form. L'Hopital's rule only deals with these two forms. And this is L'Hopital's rule. Suppose that f of x and g of x are differentiable, g of x g prime of x doesn't equal 0, and that the limit as x approaches a of f of x over g of x is 0 over 0, or the limit as x approaches a of f of x over g of x is equal to plus or minus, we don't care about the signs, infinity over infinity. Okay? If that's the case, so we have the famous 0 over 0 or infinity over infinity, plus or minus, don't care about signs. Then we have indeterminate forms. Then, and this is L'Hopital's rule, what does it say? The limit as x approaches a of f of x over g of x is equal to the limit as x approaches a of f prime of x over g prime of x. It's not the quotient rule. Let me rephrase that. It is not the quotient rule. It's what you wanted the quotient rule to be. Quotient rule is derivative the top times the bottom minus the top times derivative bottom all over the bottom squared. It was a huge function when you tried to take derivative of a fraction. This is a ratio. When you have f of x over g of x and you're doing a limit, it's equal to the limit as x approaches a of the derivative of the numerator divided by the derivative of the denominator. They go at the same rate, and maybe that'll be easier for you to plug the thing into. Because you still, number one rule limits plug in a number. Now, when is pre-section quiz due in this class for section 3.7? When is it due? Tonight at 11:30 something, right? Okay, it's due tonight. So if you haven't gotten the quiz done yet, please do so. I did these problems on the quizzes. Now I'm going to do one of them, but I'm not going to do the rest of them because I'm trying to show you something or other. You see this problem right here? Take the limit as x approaches 2 of 2x squared minus 8 over x minus 2. Now let's talk about the final exam for just a second. Because 30% of your grade is going to come from that final exam. Your life kind of depends on that final exam. You guys doing well on that thing. When we give you a problem like this, you actually have two options. You can do it the old way from chapter 1.3, or you can do it the new way. I'm going to show you the difference between the two. If I did it the old section 1.3 way, first rule of limits is to plug in the number. Plug in 2. Well, 2 squared is 4 times 2 is 8. 8 minus 8 is 0 divided by 2 minus 2 is 0. In the old way, we would have to do algebra. And I would take the limit as x approaches 2 of, I would factor a 2 out of the numerator. That gives me 2 times x squared minus 4 over x minus 2. That's equal to the limit as x approaches 2 of. I can do some more algebra because x squared minus 4 is a quote-unquote difference of squares. So how does that factor? X plus 2 times x minus 2 over x minus 2. And then the whole purpose of quote-unquote do algebra is something but a cancel. What cancels here? X minus 2 is canceled. This is equal to the limit as x approaches 2 of 2 times x plus 2. And again, I'm showing you exactly the work you had to show in chapter 1.3. And now, once you clean it up and cancel something out, and then you do the limit by, quote unquote, plug in the number. And when you plug it in, you don't write limit anymore. It'll be 2 times 2 plus 2. And 2 plus 2 is 4 times 2 is 8. Yeah, the answer, sorry, slide over. The answer is 8. Okay? But now we have this new and improved way of doing things called L'Hopital's rule. Now, I've put a lot of videos out there. I'm one of the poor saps who also made up all the solutions to the final exams. If you go to the bookstore, the UNC Charlotte bookstore, and you go in there and ask for the Calculus 1 Solutions to Old File Exams. They have a little packet for you. You can also go to, you guys know Prospector, and underneath Prospector where the post office is, there's a little print shop right beside it. They also sell them there. There's the Solutions to Calc 1, and I also made one for Calculus 2 for you guys and stuff. Now, I'm just trying to give you guys a clue here that when I'm going to do L'Hopital's rule, I always give everybody the same code. When you see me write L'H, that is my code, so get used to it. It's not required. It's not written in any textbook that all professors must use L'H. Only I do this, maybe some other people that watch me or whatever. But this is to let you guys know I'm going to use L'Hopital's rule. L'Hopital's rule, because this is 0 over 0, this will be equal to the limit as x approaches 2 of, and all L'Hopital rule it says is when you got a fraction and you got 0 over 0 or infinity over infinity, you take derivative of the top over derivative of the bottom. Let's do that. What's derivative of 2x squared minus 8? 4x. Divided by what is the derivative of x minus 2? 1. That's derivative of the numerator over derivative of the denominator. And then you, first row of limits, plug in the number. When I plug it in, what do I get? 4 times 2 divided by 1. Well, don't hurt yourself on the math. 4 times 2 is 8. Divided by 1 is 8. Now, beauty of math. There's only one answer. Now I ask you, which way is better? Better being shorter, faster, and getting the answer much cleaner, quicker. L'Hopital's rule obviously is. Okay, less work for me to do. I don't have to go beat the algebra and remember the difference of squares and stuff. I just got to know how to take derivatives. Derivative of the numerator or derivative of the denominator and plug it in. And listen to my words. You can do L'Hopital's rule as many times as you need until you get an answer. So if I got some crappy fraction and I got derivative of the top over derivative of the bottom, I plug in a number, I still got infinity over infinity or 0 over 0, I can take derivative of the top again over derivative of the bottom again. I can do first, second derivative, third derivative top over third derivative bottom. Keep going until I actually get something other. But remember, once you do the derivative of the top over derivative of the bottom, always clean up your fractions. Clean it up. If you see stuff canceling, cancel it out. Do the algebra and then plug in the number. Now, I did a bunch of problems. Please watch the pre-section videos on this thing because I'm going to come over here to the next page. And I did all these problems here, so I'm going to start with problem number 6 since I didn't do that one on the pre-section video. All right, here we go. Take the limit as x approaches negative 2 of x squared minus 4 over x plus 2. First thing you got to do is you got to plug in a number. You got to see that it's a L'Hopital rule type. And let me explain why. You know you also have problems out of your textbook. We also give you guys tons of web work problems, and I know this is mostly what you focus on, but there's some wonderful examples out of your textbook that we really want you guys to study as well as watch all the things that I do up here. Okay? Now, with that, here's the deal. You got to show your work. Now, on the textbook, we got all this whole section on L'Hopital's rule. And what students have gotten into a habit is every time you give them a limit problem in L'Hopital rule section, they just take derivative of the top over derivative of the bottom and then try to plug in the number. So they tried to fool some people by putting non-L'Hopital rule problems in the L'Hopital rule section just to see if you're checking it out. Because if you use L'Hopital's rule on something that is not a L'Hopital rule problem, it is wrong. It'll give you a wrong answer because it's not L'Hopital rule. L'Hopital's rule is only used for 0 over 0 or plus or minus infinity over infinity. So the first thing you got to do is plug it in. And you should see that. So if I plug in 2, that'll be 2 squared minus 4 over negative 2 quantity squared plus minus 4 over negative 2 plus 2. Negative 2 quantity squared is actually 4 minus 4 is 0 over negative 2 plus 2 is 0. It is 0 over 0. That's the first thing you got to check. So I'm telling you, they're going to try to fool you, and they're going to throw a non-L'Hopital rule problem, and if you did derivative top and derivative bottom, you'll screw it up. You've got to check it out first. Now, this is L'Hopital's rule. We will apply it. So this is the limit as x approaches negative 2, and you take derivative of the numerator over derivative of the denominator. What's derivative of x squared minus 4? What's derivative of x plus 2? 1. And plug in the number. That'll be 2 times negative 2 over 1. The answer is negative 4. And it gets you the answer and gets it to you quickly without having to do so much algebra. Very important rule. And again, it's a rule you'll see again and again and again as you march up the chain of all the different math classes that you got to have. Try this guy. The limit as x approaches 0, and I'm going to put this one as on the plus side. There's a little typo on that one, so I want to put it on the plus side here. What is the limit as x approaches 0 on the plus side of 1 minus e to the ax divided by x to the 7th? Well, the first thing I'm going to do is I'm going to plug it in. This will be 1 minus e to the a times 0 on the plus side over 0 on the plus side to the 7th power. What is a times 0? Granted, it's on the plus side, but who cares? What's a times 0? A is an arbitrary constant. What's a times 0? 0. What's e to the 0? So this is e to the 0, which makes it 1, and 1 minus 1 is 0, divided by 0, on the plus side, graded, raised to the 7th power. It's 0. What does that mean? L'Hopital's rule. So this is equal to the limit as x approaches 0 on the plus side of the derivative of the numerator. This is for your benefit. What's the derivative of 1? 0 minus, what is the derivative of e to the ax? Derivative of e to the x is e to the x. The derivative of e to the a times x is chain rule. Derivative of e to the ax times derivative of the exponent. So this would be e to the ax times derivative of the exponent, which is a. Does that make sense? Derivative of a times x, a being a constant. A times x, derivative is just a. Divided by, what's derivative of x to the 7th? 7x to the 6th. So I'm going to clean this up. This will be the limit as x approaches 0 on the plus side of negative a e to the ax divided by 7x to the 6th. Now what are you going to do? Plug it in. This will be negative a e to the a times 0 over 7 times 0 to the 6th power. And this officially is on the plus side. Don't forget that. What do you get? Well, let's do the math. What's a times 0? 0. What's e to the 0? So this becomes e to the 0, which is 1 times negative a is negative a. Over, here we go. What is 0 on the plus side to the 6th power? What's 0 to the 6th power? 0. What's 0 on the plus side to the 6th power? 0 on which side? Remember, it's even. Anything raised to an even power is always going to be quote-unquote positive. Right? So this is an even power here. So when you take 0, whether it be negative or positive, you raise them to the 6th power, it's going to be positive. But it's still 0, granted. But I need that sign. You'll see why in a second. So this is 0 on the plus side times 7. What's 0? Slightly positive, 0.00001 times 7. 0.00007. It's still 0 on the plus side. But it's important it's on the plus side because of that 6th power. Does that make sense? Now, what is this answer? Let me rewrite it. This is equal to negative a times 1 over 0 on the plus side. Oh no, it's that same mess I did a few minutes ago. If I figured out what I did with my little note thing there, I would actually show it to you. I did so many of these things. Hold on. Ah, there it is. Sorry. What is 1 over 0 on the plus side equal to? Positive infinity. Right. So this is equal to negative a being some constant number, times positive infinity. What is the answer to this particular problem? It's actually negative infinity. But it's one of these problems I'm trying to show you where you can kind of get a little lost at if you don't follow your nose. The answer is negative infinity for this problem. Sorry, I'm off the page there. Does that make sense? This is why I had to 0 from the plus side. So the limit as x approaches 0 on the plus side. Well, first it was 0 over 0, so we took L'Hopital's rule. But because this was an even power, when I plug in 0 on the plus side and raise it to an even power, it's still going to be 0 on the plus side. Okay? So, what about the next one? Take the limit as x approaches 0 of the sine of 10x over the sine of bx. Stole this one off web work, just to let you know. First rule of limits, plug it in. Okay. This would be the sine of 10 times 0 is 0 over the sine of 10 times 0, which is 0. What's the sine of 0? That's 0. It's 0 over 0. It's indeterminate. Well, you think, well, maybe these things cancel. Well, maybe the b, because the b is different from the 10, maybe it won't. No, no, it's indeterminate. So 0 over 0. So guess what I'm going to do? L'Hopital's rule. So this will be equal to the limit as x approaches 0 of the derivative. What is the derivative of the sine of 10x? Yeah, the sine of 10x. And what rule would I have to use? Take derivative of the sine of 10x. Chain rule. Derivative the outside, inside stays the same time derivative the inside. What's derivative of sine? Cosine. The inside stays the same, 10x, times the derivative of the inside. What's derivative of 10x? 10. Divided by, what is the derivative of the sine of bx? Catch a pattern. Well, derivative of sine, chain rule again, the derivative of sine is going to be cosine of the inside stays the same, bx, times derivative of the inside. What's the derivative of b times x? Just b. Now plug it in. This would give you the cosine of 10 times 0 times 10 over the cosine of b times 0 times b. Well, that's the cosine of 0 times 10 over the cosine of 0 times b. What's the cosine of 0, though? 1. So the answer is 10 divided by b. Web work. B will be arbitrary. You will type in 10 divide little alpha b. There you go. Does that make sense? Well, can they mess you up even further? Sure, let's try some of these weird ones. Remember all that limit stuff I wrote up for you guys a little bit ago. Very important. What is the limit as x approaches infinity of the natural log of x divided by x squared? First rule of limits, plug it in. So this would be equal to the natural log of infinity divided by infinity squared. What's the natural log of infinity again? Again, things you're supposed to have memorized from beginning of chapter 3 there. Natural log of infinity is infinity. Over infinity squared is infinity. It's infinity over infinity. That's also a L'Hopital rule style. So applying L'Hopital's rule, this is equal to the limit as x approaches infinity of, here we go. What is the derivative of the natural log of x? Have you got it memorized yet? 1 over x. What is the derivative of x squared? 2x. Do you guys remember what I said a few seconds ago about this L'Hopital's rule? You take derivative of the top divided by derivative of the bottom. And then, before you plug it in, you clean them up. You need to clean this up. Because this is a fraction numerator. 1 over x divided by 2x. And that's 2x over 1. So when you actually have a fraction divided by a fraction, you got to clean it up. You don't just go ahead and plug it in. Clean it up first. This will be 1 over x times, invert multiply, 1 over 2x. Agreed? Which actually equals the limit as x approaches infinity of 1 over 2x squared. Clean him up first, then plug it in. That's most important about L'Hopital rule. So plug it in. When I plug it in, I get 1 over 2 times infinity squared. Infinity squared is infinity times 2. So it's 1 over infinity, which is, the answer is 0. Does that make sense? Questions? Look at the next one. Take the limit as x approaches 1 of the natural log of x over x minus 1. First rule of limits, plug it in. You get the natural log of 1 over 1 minus 1. You guys remember what the natural log of 1 is? 0. Over 1 minus 1, 0. Yep, that's it. L'Hopital's rule. 0 over 0. Only 0 over 0 or infinity over infinity do you have to do this stuff. So this is equal to the limit as x approaches 1 of the derivative of the numerator. What's the derivative of the natural log of x? 1 over x. Divided by what's the derivative of the denominator? X minus 1. What's the derivative of that? 1. Clean it up. Okay, 1 over x divided by 1 is just 1 over x. So the limit as x approaches 1 of 1 over x equals 1 over 1, which is 1. Does that make sense? Look at the next one. The limit as x approaches 0 of the sine of x over 1 minus cosine of x. First rule of limits. This is why you need to know your trig. Plug it in. This will be the sine of 0 over 1 minus the cosine of 0. The sine of 0 is 0 over 1 minus the cosine of 0 is 1. And 1 minus 1 is 0. So it's 0 over 0. This is a L'Hopital rule problem. So this is equal to the limit as x approaches 0 of derivative of the top over derivative of the bottom. What's derivative of sine of x? Cosine of x. What's derivative of 1? 0. Minus what's derivative of cosine of x? Negative sine of x. I'm trying to be very careful so I don't lose my negatives and stuff like that. So what's the wonderful use of parentheses here? What's a negative of negative? So this is equal to the limit as x approaches 0 of the cosine of x over the sine of x. And then, first rule of limits is once you clean it up, plug it in. This would be the cosine of 0 over the sine of 0. What's the cosine of 0? 1 over, what's the sine of 0? What is 1 divided by 0? See, this is not from one side or the other. They didn't put a sign on this thing. Does that make sense? So it could be positive or negative. 1 over 0 does not exist. Does that make sense? I better put that in my little notes here. Okay. I'll rewrite it over here again. Remember, 1 over 0 on the plus side is positive infinity. 1 over 0 from the minus side is negative infinity. 1 over 0 when you don't have a side, because they're going in two different directions, does not exist. Oh, sorry. Does that make sense? My rules from way back when. Look at the next guy. Take the limit as x approaches 0 of a to the x minus 5 to the x divided by 9x. First rule of limits, plug it in. This would be a to the 0 minus 5 to the 0 over 9 times 0. Any a, base, obviously a number bigger than 0. Anything to the 0 power is what? 1 minus 5 to the 0 is 1 over 9 times 0 is 0. 1 minus 1 is 0. It's 0 over 0. And right here is where people are going to die because you didn't memorize the rules. This is a test that's going to really quiz you on whether you memorized all those new derivative rules, as well as this continuously product rule, chain rule, quotient rule mess. So, L'Hopital rule it. This will be equal to, and I should have put the L'Hopital rule up here again. This will be equal to the limit as x approaches 0 of the derivative. What is the derivative with respect to x of a to the x minus 5 to the x? Well, what's the derivative of a to the x? That was one of the rules you're actually supposed to have memorized. The derivative of e to the x is e to the x. But anything other than e as a base, the derivative of a to the x was what? What was the rule? A to the x times the natural log of a. Having that one memorized, because that was a rule, and this is a web work problem as well, what is the derivative of 5 to the x? What's the derivative of 5 to the x? 5 to the x times natural log of 5. Catch your pattern. Divided by what's the derivative of 9x? 9. All right. Just be careful when you guys do this kind of work, because now you're getting into the wonderful world of algebra, calculus, and a few higher level mathematics. My 9s sometimes look like A's if I'm writing in a rush. That is a 9, that is an A. Clearly you can see the difference. You will also, when I get you guys in differential equations, we're going to convert things into, from the t time world to doing Laplace transforms to something called the S world. You know my biggest problem with differential equations when I was doing it when I was in college? My S's look like 5s, and that will screw up a problem like nobody's business. So what I'm telling you is neatness counts, and it's only going to get worse. Be neater as you get higher level math. All right, next rule, plug it in. This would be equal to a to the 0 times the natural log of a minus 5 to the 0 times the natural log of 5 divided by 9. You with me? And once I plug it in, I don't write limit anymore. I'm trying to show the proper, because it's not just about getting the answer, it's about showing the work and getting it right. So what's anything a to the 0 power? 1. 5 to the 0 power, anything to the 0 power is 1. So the answer is the natural log of a minus the natural log of 5 divided by 9. There's my solution. Does that make sense? Don't lose you guys anywhere. This one is a good practice on what was the derivative of a to the x, things you're supposed to know from chapter 3.3. All right, take a look at this next guy. Take the limit as x approaches infinity, excuse me, as x approaches 0, of 1 plus x minus e to the x divided by 3x squared. First rule of limits, what are you going to do? Plug it in. Check it out first. Make sure it's a L'Hopital rule before you actually apply the L'Hopital rule principle. Otherwise, if you apply the L'Hopital rule principle on something that's not the L'Hopital rule, well, it's just all wrong. Okay? So, plug it in. This will be 1 plus 0 minus e to the 0 divided by 3 times 0 squared. E to the 0 is 1, so this will be 1 plus 0 minus 1, which is 0. 0 squared is 0 times 3 is still 0. Yep, it's 0 over 0. That tells me L'Hopital. So this is equal to the limit as x approaches 0 of, what is the derivative of 1 plus x minus e to the x? What's the derivative of 1? What's the derivative of x? 1 minus, what's the derivative of e to the x? E to the x. Divided by, what's the derivative of 3x squared? 6x. So there's my new function. Derivative of the top over derivative of the bottom. It's not the quotient rule. It's what you wanted the quotient rule to be. You just take derivative of the top over derivative of the bottom because it goes at the same rate of change. Plug it in. This is equal to 1 minus e to the 0 over 6 times 0. E to the 0 is 1. It's 1 minus 1 over 0. It's 0 over 0. So what am I going to do? Do it again. You can do L'Hopital rule. This is a L'Hopital rule twice problem. You can, as long as you keep getting 0 over 0 or infinity over infinity, you can continuously do L'Hopital rule until you actually get something right. So do it again. So this is equal to the limit as x approaches 0 of, what's the derivative of 1? 0 minus what's the derivative of e to the x? E to the x over what's the derivative of 6x? 6. So I took the derivative again. So this is a 2 L'Hopital ruler. Now plug it in. This is going to give me negative e to the 0 divided by 6. E to the 0 is 1. The answer is negative 1 over 6. Once you get a number, you win. Does that make sense? Did I lose you guys anywhere? Questions? Here's where it gets interesting. There are other indeterminate forms out there. The other indeterminate forms are 0 times infinity. Think about it. What is 0 times infinity? Is it 0? Is it infinity? Well, it depends. Okay, how fast are you going to 0 versus how fast the other dude's going to infinity is what the multiplication of this thing is going to be. So sometimes the answer is 0. Sometimes the answer is infinity. Sometimes the answer is 45. You can't tell. It's indeterminate. Another one. Infinity minus infinity. That's another type of indeterminate form. What is infinity minus infinity? For most people, it should be zero. Don't the infinities cancel out? Not necessarily. It depends on how fast or how big this infinity is versus how fast or how big this infinity is. You know, there's two different kinds of infinities out there. There's the Bill Gates infinity, and then there's the Oprah Winfrey infinity. Oh, they're both rich. But which one's richer? According to Forbes magazine. Who's got more money? Bill Gates or Oprah Winfrey? Gates does. Yeah, Microsoft crap. Okay, Bill Gates does. So if I take Bill Gates and subtract off Oprah's money, you got it? I'm still going to be an infinite amount of money. If I flip it up and take Oprah minus Bill Gates, I'm going to get negative infinity, a negative infinite amount of money. Does that make sense? But then there's other types of infinities, the Clinton infinities. Bill Clinton versus Hillary Clinton. Well, they're both rich. Okay? Which one's richer? I don't know. Let's see here. There's Bill Clinton. He's got an infinite amount of money. There's Hillary Clinton. So if they got divorced or something or other, infinity minus infinity is zero. But maybe zero. They're basically close to the same amount of money. But I think Bill, because he's been retired a little bit longer, has about $45 more than Hillary does. So infinity minus infinity could be 45. My point to this exercise is infinity minus infinity, you can't tell what's going on because it really depends on the size of the infinity, and you can't tell that by just an infinity symbol. It's indeterminate. We're going to put these things into classes in this particular section. This is your first class, the 0 times infinity indeterminate form. The infinity minus infinity is your second class. The third class is going to be all three of these other guys put together. Other indeterminate forms. What is 0 raised to the 0 power? Anything to the 0 power is 1. But what if it's 0? 0 to any power should be 0. So is it 1 or is it 0? Yes. Sometimes it's 1 and sometimes it's the other. I can give you examples of both that. Sometimes the answer is e to the 12th. I'll show you examples of that later. Infinity to the 0 power. Is that infinity? But anything to the 0 power is supposed to be 1. Is it going to be infinity? Is it going to be 1? Or is it going to be some number in between? Like e to the negative 5. Yep. And the famous 1 to the infinity. Now you're thinking 1 to any power should be 1. Yeah, but remember, we're doing limits. So you're going towards 1 as the exponent is going towards infinity. Is that going to be 0? Is it going to be infinity? Is it going to be 1? You can't tell. Indeterminate forms. But the deal is, you see all three of these guys? These are a pattern. All three of these last terms are exponential indeterminate forms. And exponential indeterminate forms, I'm going to group those guys together, and we're going to approach those in a different way to be able to handle those. So all these guys are grouped together. So the first type is here. So let me give you the hint on the first type. Hint. Remember, to be able to use L'Hopital's rule, you've got to have 0 over 0 or infinity over infinity. So the trick, when you have 0 times infinity or infinity times 0, that means you actually have a product. To be able to do L'Hopital's rule, you've got to have a fraction. So we're going to play algebra games on this one. So if you got a product of two things and it makes it 0 times infinity, you're going to take one of the two guys and put him in the denominator. But to be able to put him in the denominator, remember the original problem is multiplication, you're going to have to do it something like f of x divided by 1 over g of x. Because when you divide by a fraction, you invert multiply, right? So this and this are the same thing, but if you don't like putting the g in the denominator, fine, put the f in the denominator. It doesn't matter. You're going to put, well, it actually does. We'll see you later. But you're going to put one of these guys in the denominator to make a fraction. And when you got a fraction, numerator, denominator, that's when the L'Hopital rule is going to show up. So we're going to convert the 0 times infinity to basically a L'Hopital rule type. You're going to have to do algebra on this thing to turn it into this stuff. Does that make sense? I will do this on Tuesday's class. So I'll finish up section 3.7 and I will move on into section 4.1 because, hey, this is calculus, is what we do. But remember, Thursday is when your homework set is due and the following Tuesday is going to be your test on that. Also on Friday, we're going to go over web work. Tomorrow, we're going to go over web work as well as if you got questions on your homework set, we'll be happy to go over and give you hints and maybe even help you out with a lot of those problems. So see you guys then. Thank you.
It's on